regular pattern in it, it would aid in the process of cryptanalysis. Of course, those that cryptographic algorithm can serve as the core of the PRNGs. So the three broad categories of the cryptographic algorithm are commonly used to create the PRNGs. One is the symmetric block ciphers, asymmetric ciphers, and the third one is the hash function and message authentication code. So any of these approaches can yield a cryptographically strong PRNG. A purpose-built algorithm may be provided by an operating system for general use. For algorithms that already use the certain cryptographic algorithms for encryption or authentication, it makes sense to reuse the same code for the PRNGs. So the next we look at the stream cipher diagram here. Okay. A typical stream cipher encrypts the plain text 1 byte at a time. So it takes 1 byte, it do the encryption, and then the next one. Although a stream cipher may be designed to operate on 1 bit at a time or 1 unit larger than a byte at a time, if you look at figure 2.7 is a representative diagram of stream cipher structure. So if you look at this structure, a key is input to a pseudo-random bit generator that produces a stream of 8-bit numbers that are apparently random. Okay, you call it random. The pseudo-random stream is unpredictable without knowledge of the input key, and has an apparently random character. So the output of the generator called a key stream, right? We call it key stream, is combined 1 byte at a time with the plain text stream using the bitwise exclusive OR operation. Okay, as you can see in the figure, here we have the encryption, and here we have the decryption. Encryption, plain text, plus the key, and pseudo-random byte generator. Okay, and then we do the encryption and generate the ciphertext. And in the other side, the ciphertext to the algorithm exclusive OR, that is the bitwise exclusive OR. With the key, which is a pseudo-random byte generator, we can get out the plain text byte stream. That is basically we call it the stream cipher diagram. Okay. So the KUMA, we call it the KUM 897, lists the following important design consideration for a stream cipher. We're going to talk about the stream cipher considerations. The first one is the encryption sequence should have a large period. A pseudo-random number generator uses a function that produces a deterministic stream of bits that eventually repeats. The larger the period of repeat, the more difficult it will be to do the cryptanalysis, of course. The second one is the key stream should approximate the properties of a true random number stream as close as possible. For example, there should be an approximately equal number of ones and zeros, for example. If the key stream is treated as a stream of byte, then all of the 256 possible keys values should appear approximately equally often. So the more random appearing the key stream is, the more randomized the ciphertext is, making more difficult to cryptanalysis. Okay. So on the number 3, note from figure 2.7, we referred to it last time, the output of the pseudo-random number generator is conditioned on the value of the input key. Right, to guard against the brute force attack, the key needs to be sufficiently long. The same consideration as apply for block cipher are valid here. Okay. So with current technology, a key length of at least, we discussed just now, at least 128 bits is desirable. Okay. So in few slides back, we discussed about the RC4, right? We mentioned the RC4. The RC4 is a stream cipher designed in 1987, okay, by Ron Rivers for the RSA security. It is a variable key size stream with a byte-oriented operations. The algorithm is based on the use of a random permutation. Okay. The analysis shows that the period of the cipher is overwhelmingly likely to be greater than 100 about. Okay, so that is about the RC4. So it is used in the secure socket layer, transport layer security, SSL or TSL standards that have been defined for the communication between the web browser and the web server. Okay. So the RC4 algorithm is simple and quite easy to explain, if you want to say. Okay, a variable length, the variable length key of from 1 to 256 byte, okay, is used to initialize a 256 byte state vector S with the element S0, S1 up to S255. Okay. We don't want to explain here in more details. Okay. So here look at the RC4. This one illustrates the RC4 logic, in fact. Okay. So a symmetric block cipher processes one block of data at a time. So we discussed about the stream. Here is the cipher block modes of operation. In the case of DES and 3DES, the block length is B is equal to 64 bits. For AES, the block length is 128 bits. So that is the difference between these two, right? The AES, we said 128 bit minimum, and the 3DS is 64. For longer amounts of plain text, it is necessary to break the plain text into smaller pieces, right? We call it into B-bit blocks. To apply a block cipher in a variety of applications, 5 modes of operation have been defined. The 5 modes are intended to cover virtually all of the possible applications of encryption. So these modes are intended for use with any symmetric block ciphers, including the triple DES and AES. So later we will discuss about these 5 important modes. Okay. So the simplest way to proceed is using what is known as electronic code book, right? That is the first mode, in which the plaintext is handled B bits at a time, and each block of plaintext is encrypted using the same key. So the term codebook is used because for a given key there is a unique ciphertext for every B bit block of plaintext. So therefore, one can imagine a gigantic codebook in which there is an entry for every possible B-bit plaintext pattern. Okay, we call it ECB. So with ECB, if the same B-bit block of plaintext appear more than once in the message, it always produces the same ciphertext. This one you should take into consideration. Because of this, for lengthy message, the ECB modes may not be secure, because the same pattern use the same process. If the message is highly structured, it might be possible for a cryptanalysis to easily exploit it. For example, if it is known that the message always starts out with certain predefined fields, then the cryptanalysis may have a number of known plaintext ciphertext pairs to work with. If the message has repetitive elements with a period of repetition, a multiple of, for example, B bits, then these elements can be identified by the analyst very easily. So to overcome the security deficiencies, we call it deficiencies of ECB, We would like a technique in which the same plaintext block, if repeated, should produce different cipher block. That is necessary to be considered. Okay. So in the cipher block chaining, or CBC, the input to the encryption algorithm is the exclusive OR of the current plaintext block. Okay. And the preceding ciphertext block, the same key is used for each block. In effect, we have chained together the processing of the sequence of plaintext. The input to the encryption function for each plaintext blocks bears no fixed relationship to there is no relationship to the plaintext block. So for decryption, each cipher block is passed through the decryption algorithm. The result is exclusive OR with the preceding ciphertext block to produce the plaintext. So to produce the first block of cipher, because we do not have any initialized things. So an initialization vector, or IV, as you can see at the beginning, is exclusive OR with the first block of plaintext. And on decryption, the IV is exclusive OR with the output of the decryption algorithm to recover the first block of the plaintext. Okay, because here we use a initialization vector, we call it IV. The IV must be known to both the sender and receiver. Both of them must know the IV. For the maximum security, the IV should be protected as well as the key. If you can simply send it, the opponent also can take this information. This could be done by sending the IV using the ECB encryption. One reason for protecting the IV, if an opponent is able to fool the receiver into using a different value for IV, then the opponent is able to invert the selected bits in the first block of the plaintext. Somehow, if the opponent or the attacker can convince, the receiver to do that, then can get this information, right? So it must be secure as well. So it is possible to convert any block cipher into a stream cipher by using the cipher feedback, or CFB mode. Okay, we call it the cipher feedback, CFE. A stream cipher eliminates the need to pad a message to be an integral number of blocks. Okay. So it also can operate in real time. That if a character stream is being transmitted, each character can be encrypted and transmitted immediately using a character-oriented string cipher. Okay. So if 8-bit characters are being transmitted, each character should be encrypted using 8 bits, for example. If more than 8 bits are used, transmission capacity is wasted, because here we use the 8-bit. Okay. So if you look at figure 2.10, you can see the CFE scheme. It is assumed that the unit of transmission is S bits. Okay. A common value is S is equal to 8. So with the CBC, the units of plaintext are chained together, so that the ciphertext of any plaintext units is a function of all the preceding plaintexts. Okay, that's why we call it the S-bit ciphertext feedback mode. Look at the, of course, guys, this is not in your exam, but anyway, you should be familiar with this thing. So that's why I explain a little bit more in detail. So we have the counter mode, CTR. Look at the encryption and the decryption. So as you look at figure 2.11, a counter equal to the plaintext block is used. The only requirement is that the counter value must be different for each plaintext block that is encrypted. That also is the CTR. So let's look at the advantages of the CTR modes is the hardware efficiency. Unlike the chaining mode, encryption or decryption in CTR can be done in parallel on multiple blocks of plaintext or ciphertext. For the chaining mode, the algorithm must complete the computation on one block before we start the next block. So this limits the maximum throughput of the algorithm. Okay. But in CTR mode, the throughput is only limited by the amount of number of the way parallel that is achieved. The second one is the software efficiency. Similarly, because of the opportunities for the parallel execution in CTR. So take into your consideration, take note that